It worked the first time. That's good. What does it mean when you say sine squared of 2t? What are we actually squaring? The n? The sin? Or what? Yeah, the whole sine of 2t, right? So this is review, but you know, the sine squared of x, that's the condensed version. If we're going to use it, it's kind of nice to write in the expanded version like that. So we're squaring the whole thing, yeah. So when you plug in, you get sine of 0, which is 0, squared is 0 over 0, right? And again, it's kind of helpful to realize what's causing the 0 in the top and bottom. There's actually 2 factors of sine in the top causing 0, and 2 factors of t in the bottom causing 0. So here's what I would recommend. Let's separate them. We got sine of 2t over one of the t's, right? And then we'll do the whole gel cell thing again. And then we got another sine of 2t factor and another gel cell. And then out here in wimpy parenthesis land, is anything left? Yeah, 3 in the bottom, right? So 1/3 essentially. And now, again, we can go back to creating what we need, which is a 2 down here. So I'll put a little 2 factor there. And then I need another 2 down here, so another 2 factor there. All right, so kind of the same idea here, splitting it up, associative property multiplication. And now, of course, it becomes 1 times what? 4/3. Yeah, so the answer is 4/3. So that's how I would recommend doing it. Some people get overly confident with something like this, and they'll do this. They'll say, okay, it's sine squared of 2t all over t squared, and then they put the 1/3 out here, and they're like, okay, I need a 2, and they'll put a 2 there, and then they'll put a 2 here, and then they'll call that 1, right? And that doesn't quite work, does it, even if it's squared? Because they didn't split it up, they didn't square the 2, so just be careful. If you want to split it up, that's nice, but I understand if that were like sine to the 20th power, you probably wouldn't want to build 20 gel cells, right? But that's the idea. So just be careful, create what you need, and then use what we memorized. All right, here comes J. It's all yours. It's all yours. However you want. Memorization, guess and check, manipulation, create what you need. Uh-oh, critically low. Yeah. Yo, you plugged in. Good. Yep. Yeah. So I'm walking around and I'm definitely seeing that if this were a multiple choice question, I would definitely want to put 2/5 as an answer choice. Definitely. Maybe even answer choice A. So it's the first thing you read and like, there it is. And then you move on to the next, right? Yeah, 2/5, right? 2/5. Aha! Did you look down for that one? Is that down there? No, you figured that one out. Good. Yeah. Yes. Oh, that one?
I don't know why I keep doing it. We'll get there.
Yeah, we'll get there. There, good. Splitting it up. Yeah. So in this one, if you split it up, you're not going to make, I would say, the careless mistake. Because, yeah, 2/5, you could first of all do it by the way we memorized it, right? This would fall under the limit as x goes to 0. You do get 0 over 0. And so any combination of sines or cosines, it's just going to be 2 over 5. But everything is squared here. So you either do one of two things. You either split it up, sine of 2x over sine of 5x, times, and then you do another one, sine of 2x over sine of 5x. And now you can use the rule that says that's 2/5 times 2/5, which actually gives you 4/25. That's one way to do it. Some of y'all were actually then splitting it up and creating what we needed. And that's kind of fun to do. but it does take a while to actually go back and do, where did we do it? Right here. It takes a while to create what you need. Right here, yeah. So that's fine if you still want to do it that way. The other way to do it is to realize that the whole quantity, because both of those are squared, you can write that as sine of 2x over sine of 5x, and you can use the properties of exponents that says the whole thing is squared. So if you do it like that, then that's 2/5 quantity squared, and it comes out to be 4/5. So anyway, be careful, because some of these answers are designed not only to test to see if you've memorized things, but also to kind of bait you into easy answers psychologically. All right, this one here. Let's see, is that the one? Yeah. This one here. Never not first, right? Never not first. What do we get when we plug in? We get e to the 0, which is 1. Cosine of 0 is 1. 1 squared is 1. So if that's all we get in the numerator, we know now for sure this is not indeterminate form. It's going to work. Secant of 0 is what? It's also 1, right? Secant of 0 is 1. So 1 times 1 divided by 1 is 1. Yeah. So it looks complicated, doesn't it? It looks like it's going to be some kind of like group and imprisonment and whatever, but it's not. It's direct sub. So might you have one on a test where direct substitution works? You might, right? You might. So the good news is if you didn't do direct sub first and you started manipulating it using the correct identities, you're still going to get the same answer, right? That's how identities work. But you're squandering time, and maybe time to practice that is somewhere else. Okay, so let's do this one. H-I-J-K-L. We're getting through the alphabet here. We're approaching 4 from the right, but we can still try direct substitution, find the general limit. So if I plug in, I get 4 minus 4 is 0. Tangent of 0 is 0. Plus 8 minus 8 is 0. So I get 0 in the top, and what do I get in the bottom? 4 squared is 16. 16 minus 4 is 12. So I get 0 over 12, which is what? Is that the answer? Kevin, is that the answer? Yes, that is the answer. That is the answer. Direct substitution works, okay? So that's maybe why it wasn't working out for you, Kevin, because you were trying to manipulate it into something. Now, what are some of our options if we did want to manipulate it? Since it's 2 terms, you could put each term over the entire denominator, and then maybe on that one there, you can, well, that's not even going to give you 0 over 0. So you couldn't even get a Jumpman thing going because this would be x plus 2, x minus 2, and if you factor the 2 out, it's x minus 4. So some of these things are created to entice you in a certain direction, but never not first what? Direct sub. Okay, direct sub. All right, so that takes care of that. And again, if you want to memorize this, which brings us kind of to the last part here. When all else fails, you just have to be clever, okay? So 16 is just general cleverness. Now, it's pretty clever if you come up with it on your own, but once we kind of talk about how to do a problem, it just becomes another strategy, right? So let's look at this guy here. The limit as x goes to 0 of 5x squared over 1 minus cosine. Looks harmless, right? Direct sub gives us 0 over 0. Yeah. Now it looks like maybe we can use the cosine one that we memorized, yes? So let's kind of review that off to the side. The one that we memorized was the limit as x went to 0. We memorized 1 minus cosine of x over x was equal to 0, right? That's what we memorized. And we also know that if we flipped that one, it gave us what? The reciprocal of 0 is some type of infinity, okay? So let's see if we could do that. There's an x squared in the top. So if I split it up and call that 5x times, and then I leave that x and 1 minus cosine of x, again, just using the associative property of multiplication. Now by direct substitution, 5 times 0 is 0. And of course, I know the other one now, because it's the flip of the one I memorized, is some type of infinity. Oh boy, I have 0 times infinity. That is a great tug of war, isn't it? Infinity is pulling it infinitely large in magnitude, and 0 is pulling it infinitely small in magnitude. Who's going to win that tug of war? You think 0 wins? 0 is pretty powerful, right? But up against infinite power? Well, let me show you something. How are 0 and infinity related? They're reciprocal. So if I put this over 1, if I bring 0 to the bottom, I get plus or minus infinity over the reciprocal of 0 is infinity. Or if I leave the 0 in the top and I bring the infinity to the bottom, the reciprocal of infinity is 0. So really, 0 times infinity is just another version of 0 over 0 or infinity over infinity, which is what? No. It could be 1. It's indeterminate. That's what this whole section's about, right? If we get 0 over 0, there's a hole there, and we have to figure out the y value of the hole, which could be at 1, or it could be at 7, or it could be at peaches. We don't know. It's indeterminate. So 0 times infinity is another indeterminate form. Later on in the year, when we learn L'Hopital's rule, we'll learn a bunch more. So there's a third one, okay? 0 times infinity. There is a tug of war going on, and the winner could be 1, the winner could be 7, the winner could be 0, or the winner could be infinite still. We don't know. So this method is not going to work, okay? It's indeterminate. So let's go ahead and take all of this and not erase it, but just, space bag it and put it under the bed. All right. So we got to try something else. General cleverness. Think back to if this were a trig proof back in the pre-cal days. What were some of our options when we had like 1 minus cosine? It was one of the things we did quite a bit of. Yes, we multiplied by the conjugate because remember, multiplying by the conjugate typically set up then a difference of squares, which led to a Pythagorean substitution. Okay, now that's asking you to think back to pre-cal proofs, the trig proofs. Let's see if it works, okay? The other method didn't. So I'm going to be left with 5x squared times 1 plus cosine of x in the top. I'm going to choose not to distribute yet until I think I need to. But by design, the denominator is going to have some things happening, right? The difference of squares, that leaves to 1 minus cosine squared. And just like if it were a trig proof, what is 1 minus cosine squared then? Sine squared, yeah. So let's go ahead and quickly review the Pythagorean identities. They are on my home page, but here they are real quickly. Cosine squared plus sine squared equals 1. That's Papa Pid. And then 1 plus tangent squared is secant squared. And then 1 plus cotangent squared is cosecant squared. So make sure you still know those. All right, so now that I change it into sine, let's try direct substitution again. If I plug in a 0 now, I get 5 times 0 is 0, and then 1 plus cosine of 0 is really 1 plus 1, that's 2. So we still get a 0 in the top, and it's caused by the x squared. And now I plug a 0 in the bottom, and sine of 0 is 0, and 0 squared is 0. So I still get a 0 in the bottom, but now it's caused by sine squared. Is that something we can deal with? Yeah, in fact, we already did, right? The first one we did after lunch was very similar, but it was in terms of t. So now we can split it up. We could do bad guy over bad guy, x over sine of x, and then x over sine of x. Give them each their own beefy bracket jail cell. And then who's left outside? Looks like we got a 5 times 1 plus cosine. All right, so we couldn't flip the cosine one. It gave us infinity. This time 0 is indeterminate. But now I know that I can flip the sine one, and these are still 1. So I get 1, 1, and then by direct substitution, I get 5 times what? 2. Cosine of 0 is 1, 1 plus 1 is 2, so the answer comes out to be 10. All right, so general cleverness, when you get an indeterminate form, and you have like 1 plus or minus a trig function, or a trig function plus or minus 1, here's a strategy that might work. Multiplied by the conjugate over the conjugate. So this is not rat-con, this is just con, right? Con. Comments or questions on that one? It's all pretty fun, right? It's better than Sudoku, doing this stuff. Yeah. All right. Let's do this one. It looks like it's going to be, let's see, the leading coefficient on the top is 3, the leading coefficient on the bottom is 1, so it's going to be some type of 3, right? Right? Oh, no. It would be some type of 3 if the limit was x approaching what? If I look at leading coefficients, that's when we're approaching infinity or negative infinity. I'm approaching 5, okay? So I did it on purpose, right? You get excited, you recognize the form that maybe he was asking a different context. So always read carefully. We're approaching 5. Let's try direct sub. You plug in the top and you get 0, and you plug in the bottom, oh boy. 25 minus 50 is negative 25, plus 25 is 0, the square root of 0 is 0. All right, we get 0 over 0. Hey, remember the first method, the factor and divide out method? This is a polynomial right here, yeah, under the radical. I just plugged in a 5 and got 0. So what that means then, in terms of that polynomial, is there's a factor of x minus 5 under the radical, yeah? And I know the top, I could then pull up the 3 and get x minus 5. What would the other factor be in the denominator under the radical? Another x minus 5. So that would be an x minus 5 squared. Does that help us? I think so, right? I have a 3 times x minus 5 in the numerator. What becomes of the denominator? X minus 5. And then these divide out. And the limit of a constant is a constant. Does that feel right? Or does that feel naughty? Huh. Ah, very good, very good. This is not correct. Okay, this is not correct. Although it feels kind of correct, it doesn't feel totally correct. It comes down to this right here. Okay, that is not just x minus 5, right? Because notice whatever value of x that you plug in here, besides 5, you're going to square it and take the square root of it. It's going to be positive, right? Can we say the same thing about what we just replaced it with? Plug in any x, do you get a positive number? No, if I plug in like a 4, I get a negative 1. Whereas if I plug in a 4 up here, I get a positive 1. So that's overgeneralization. So I think we talked about this earlier. There's an identity. The square root of x squared, which is kind of what we have, is equivalent to what? The absolute value of x. When you square it under the radical and then take the square root, it's exactly the same as the absolute value of x. So again, let's kind of take this, space bag it. We'll put all our mistakes under the bed in the space bag. How come it won't shrink down? Shrink down. There we go. There we go. So now I can replace it. I surely can replace it. But I'm going to replace it with the absolute value of x minus 5. And now it is, hola, señor trepador. So, falta. That's Jumpman. That's Jumpman. That was Jumpman in disguise. Okay, and we're approaching the 5, which is the value that gives us 0 over 0. And it's a general limit, not like the one in the warm-up where I forgot to put a one side on. It's a general limit, right? And so what's the answer? It's DNE, right? Had it been a one-sided limit, no problem. You would have just do our little trick. This is only Jumpman. There's no other factor in there. So then you could just plug in a number to the right or to the left of 5 to get the value, okay? So there it is. It's not general cleverness anymore. It's basically just a strategy using that identity. If you ever have the square root of something squared, replace it with the absolute values, okay? It was 3 from one side and ends up being 3 from the negative 3 from the other side, okay? And those aren't the same, so the general limit is undefined. Okay, comments, questions on that one? All right, how about this guy? Look what we're approaching. That's weird. Pi fourths. So you plug in a pi fourths. Tangent of pi fourths is 1. 1 minus 1 is 0. And then sine and cosine of pi fourths are exactly the same, right? They're both square root of 2 halves. So when you subtract them, you get 0. All right. Do you think we're going to be using the two trig limits that we memorized, sine of x over x and 1 minus cosine x over x, in this problem? I don't think so, right? Because for those, we had to be approaching what? 0. Here we're approaching pi fourths. Now remember, we could use those that we memorized at pi fourths, but remember we looked at that, we would have to shift it over. It would have to be like sine of x minus pi fourths all over x minus pi fourths. And I don't see any shift going on because those are just plain old x. So we are not going to be using what we memorized. So what else can we do? We can use the identities, right? We can use the identities. What was 1 minus tangent? Was that secant? No. We can't even use the Pythagorean identities because they're not squared. Maybe we can multiply by 1 plus tangent over 1 plus tangent. Maybe. But what might you do first? Yeah, probably put it in terms of sine and cosine, right? That's kind of where we're comfortable. That was kind of the ultimate strategy. So let's just do that. Let's just call tangent sine x over cosine x. And on the bottom, we'll leave it as sine x minus cosine x. And now it's like, hooray, hooray, hooray. We just created a complex fraction, which means the next step is a no-brainer. Yes, it is to get rid of the complex fraction. And to do that, we'll do lick'em over lick'em. So cosine over cosine. And I'll put parentheses around this and this. And now on the next line, we still write the limit as x goes to pi fourths. All right, distributing in the numerator, I get 1 times cosine is cosine. And then I get minus, the cosines divide out, and I get sine. Now in the bottom, do you want to distribute the cosine? No, I wouldn't. So I'm just going to leave it as sine x minus cosine of x times the cosine. And now if you plug in, you're going to get 0 over 0. Darn it! But now what's causing the zeros on the top and bottom? The two differences, right? Do they divide out? We can pull out a -1. We saw that little trick yesterday. So you can either take a full line of writing and factor a -1 out of the top or the bottom, or you could save a little bit of time and just say, and put a -1 residual there. That's a little bit faster, okay? We just got rid of the 0 over 0 problem. We now have made the world safe again for direct substitution. So if we plug in, we get -1 over cosine of pi fourths. And would that be okay for a free response answer? Yeah. We could also write that as negative secant of pi fourths, yes? That would also be a good free response answer. We could also write that, let's move this way. There's lots of different versions. Cosine of pi fourths is square root of 2 over 2. We can write it like that. Or we can write it like -2 over the square root of 2. If you want to stay, change, flip. But of course, what would be the multiple choice answer? Probably none of those. What is the reciprocal of square root of 2 over 2 when you rationalize and simplify? Well, just the square root of 2, right? Yeah. So we could verify that. Multiply by square root of 2 over square root of 2. And you're going to get -2 square root of 2 all over 2. And then, of course, those 2's divide out. In fact, I think someone in here on our unit circle quiz did not divide out the 2's and asked if it was still okay. And I was like, sure, today it is. Because it was like National Foot Massage Day or something. And so on those days, I typically accept those types of answers. So there it is. That would be the multiple choice answer. Was it you that forgot to divide out the 2's? I'm trying to remember. No? Okay. So anyway, there you go. What did we do there? We just jump-started the problem by using the identities, right? Complex fraction, fix it, plug in. Just make sure that all the while you are aware of who is causing the 0 over 0. Because ultimately, that's your goal. You're going to get rid of it algebraically, or you're going to get rid of it by memorizing the sine x over x and the 1 minus cosine x over x, and you're going to replace it with what you memorized, okay? So we'll stop right there for today. We got 2 more to go. Tomorrow we'll take a quick look at the next section, and we'll talk about the test, which will be on Friday. Still pushing for a Friday test, so anyway, that's it. Quiz tomorrow, should we? Maybe. I don't think we have time. I really don't think we have time. Quiz Friday, right before the test? That'd be a good warm-up. Saturday.